Well, welcome back. So here's the topic for today, matrix multiplication. And there's a lot of really interesting things in this, and some things that are actually, they're more difficult than they appear they ought to be. Okay. In particular, when we get and look ahead to Cholesky factorization, we factor a matrix and want to know, well, what's the non-zero pattern of the result before we compute it? That's an important thing important question to answer. It turns out that so Cholesky factoring a matrix, you may think, oh, that's a very complicated problem. There's more work to do. There is a lot more theory there. But what's interesting about that problem is that that's actually easier complexity-wise, algorithmically, in terms of time complexity, to compute the pattern of the result, the non-zero pattern of the result, than is matrix multiplication. Matrix multiplication is much actually, you can't get substantial speed up asymptotically in doing that. So matrix multiplication. So we've got C equals A times B, okay, and we need to respect the data structure, okay. Even if we choose to change the data structure, well, we may pick the wrong data structure if we do that. Okay, we want to pick an algorithm that's hopefully order flop count time proportional to the floating point operations, or not much more than that. And we want to. So we've got a lot of flexibility with matrix multiplication. I'm not going to use Strassens or all that jazz. That's actually not really very useful for sparse matrix computations. We want to access A and B column by column. So what we're going to do is use this block matrix idea. So first of all, what we can do, we've got A times B. We can write that as A. So this is, let's see, what sizes am I going to put on, or do I put on these matrices? I don't know if I do. If it really much matters what I call them. Okay, this is M by K. Now, what I'm going to first do with A is not block it at all. I mean, it's just going to be a single block. Okay, so it's not sliced and diced at all. And then C, the B matrix, will be K by N. Okay, so what I want to do is take the matrix A and take the matrix B. I'm not going to slice up A at all. So A is a single block. And so that means I can't block up the columns of B, but I'm going to slice you can't slice the rows of B, but I'm going to slice B into n different columns. Okay, so I have a block matrix times a block matrix, and I have one block here, one block there. And so what that means, if this is, say, B1, B2, and so forth, B to B sub n, you notice I'm using one base notation, and this is A, then this gives me the matrix C, and the matrix C will be blocked, if I follow this format here, will be the rows of C will be blocked the same as A, so they aren't divided at all. And the columns of C are divided up in the same way that columns of B are divided. So we get a matrix that looks like this for C. So C is a sliced up matrix by column, which is kind of handy because it's a column oriented algorithm. That's good. This will be C1 through C sub n, and this is the matrix. That's the matrix C. And so what this means is, for example, C1 is just AB1. And so in general, Cj is A times Bj. So we've subdivided the problem so that I can write the matrix C as AB1, AB2, all the way to AB sub n. We've split the problem into n completely different problems, sparse matrix times sparse vector, and that's convenient because I've got B stored as a collection of sparse vectors. So now I don't have to worry about matrix multiply. I can worry about matrix vector multiply, where A is now stored by column and B is stored by column. All right, so now let's do yet another layer. So it's blocking inside blocking. So now let's look at A. I'm going to take A and slice it by one block and K blocks here. So I've got A1, maybe I should call it lowercase, A1, A2, and so forth. And now I'm going to just multiply. I'm just going to call this matrix the vector B now. Okay, so I'm going to use the notation B1 now to refer to the first entry, the scalar. B1 is now a scalar inside the vector B. Don't confuse B1 with this B1. Sorry if I'm doubling up on notation, but hopefully that's clear. All right. If it's not, complain, please, because this shouldn't be vague. So if I slice up A now by its columns, I have to do the same to B. So now B is a collection of scalars. Okay. Now if I do the block matrix multiplication of this block matrix times this block matrix, you notice over here, you just, put your finger down, right? And you just go through and, well, that's just one item. There's no summation here. That's why I got an independent problem. Think of this, right? If you were to write down, let me back up. If you were to think of A as a scalar, and if you have a row vector B1 through Bn, well, then the resulting matrix C is just this, right? So of course, it's a block matrix, so you have to, A times B is not equal to B times A, but other than that, you can pretend, and you get this answer here. So there's no summations here. They're independent problems. Over here, though, if I think of this now as A1, A2, A3, all the way to A sub K, multiplied by this vector, B1, B2, B sub K. Okay, this is now an algebraic picture of what I've just drawn over here. And now to get C, the single result C, which will turn out to be a vector, column vector, I have to do, just put your finger down here and go and do a dot product. Right? So it's a summation of I think I have to use the letter T now. T equals 1 through K of AT times BT, where an A is a column and B is a scalar. Okay? So that's what I've got to do right here. And that's handy because I'm accessing A sub T is a column. Well, A is stored by columns, so I have easy access to the columns of A. And B is a scalar, and that may seem like a problem, but if we back up a bit, we realize that, well, I can go through and do the summation here in any order I choose. Yeah, thank you. Any order I choose, I can do this summation. So it doesn't matter. I'll get to your question in a second. It doesn't matter, for example, the entries in the column of B can be out of order. Okay, the summation, you can add things in any order. And so I'm going to take a sparse column times a scalar now as my core operation. So yes, Devya.
Yeah. I was just confused as to what this B indicates. Is it scalar or form?
Well, now over here it's, okay. I've drawn a line, okay. Over here, B1 through Bn represents column vectors. And all the B subscripts are all columns, and the capital B is a matrix. Over here now, I've thrown away the columns of B. I just have one column. So over here on this side of B is a single column, and B1 is a scalar. And BK is a scalar. And it's a different B1. This B1 and this B1 are not the same. And I'm just doing that just to save chalk, right? I could write B11 and B1, but that gets kind of tedious. Okay, so this B1 is not the same as the other B1 over here. This B1 is the first column. This B1 is the first scalar of whatever column it is I'm looking at for the vector B. Okay, so this is what I've got to compute. And this is kind of handy because we can now look at this and ask the question. I'm going to erase something. I'm going to erase this piece right here, because so you already see how we're going to. If you know how to do this over here, matrix times vector, then you just glump all of them together, do a bunch of them, and you get the matrix times matrix. Okay. So I just have to do this for every column of B, and so that's the easy part. So let me erase this. So I have independent problems. Although I'm going to exploit the fact that I'm doing lots of matrix vector multiplies. I am going to exploit that to simplify the runtime, but that's another story. That's kind of a cute trick, but you'll see that as I get there. So I have this summation. Now let's think about the non-zero pattern of the result. Let me call it script C, and now I'm looking at columns, a single column of C equals A times B, or B is a little lowercase, so it's a vector. Numerically, I have this thing. Or I've got the teeth column of A and the teeth scalar of B. And so if we, again, the mantra is, I hate to use the word mantra, but the thing I'm repeating is ignoring numerical cancellation, right? 3 minus 3 is non-zero. So we have to ask ourselves the question, what is the non-zero pattern of C? Where do things become non-zero? Well, think about what happens, and let's look at this picture over here. Suppose I've got B1 is non-zero, and suppose B5 is non-zero, and suppose B7 is non-zero. Okay, and suppose that's it. Then what's going to happen in the matrix vector multiply is that only those values of T need to take part. Right? I can just do this T from 1 to K can be the following. I'm going to change this to, well, all I'll have to do is do T in and I have to try to do this as a calligraphic. How does that work? Let's see. Is that a script B? How do I do a script B? Well, whatever. Okay, if I let script B be the non-zero pattern of this result, that is, script B is the set 1, 5, 7, then that's the only thing I have to iterate over for the value T. I just have to do the summation over the non-zero pattern of B. Well, that's handy because I have the non-zero pattern of B as a column vector. I just have to iterate through those row indices of the vector B. And then take that non-zero value, multiply it by this column vector, and then sum it into C. And so the non-zero pattern is the set union of, if I let script T be the non-zero pattern, of AT, that is to say A star T, if I want to put it in more specific notation, the non-zero pattern of the teeth column of A, which I have. So all I've got to do is do a set union of a bunch of sets, and that gives me the non-zero pattern. And the sets I choose are these right here. So this is the non-zero pattern, and these are the values. So to do this, there's several ways of doing it. You can compute this first and then compute this. You can compute it at the same time. In the code we're going to look at, I'm going to compute them at the same time. But there's other ways of doing it. Now, this is computing a set union and computing that summation of sparse column vectors is something that's very convenient to use something called scatter-gather. And this is a common theme inside sparse matrix algorithms where we temporarily use a size order n workspace and just use pieces of it. So I'm going to temporarily store C as a complete full vector. Okay, it's dense. I'm just not going to use all of it. So I don't have to spend time proportional to, let's see, what is my dimension on C? What did I call it? M? So I have a vector of size m, which conceptually we can think of this vector as being all 0, but I don't actually have to have it all 0. I can initialize it as I go, but let's pretend for the moment that it's all equal to 0. In fact, I think that's the way my code does it. So let's initialize this vector to 0. So oops, I just lied. I just spent order m time, all right, to set that thing to 0. We'll come back to that. Let's pretend for the moment we don't have to worry about this, and we won't when I'm done. So we have a vector that's all equal to 0, and so now all I have to do is iterate through all of these columns, and for any given, so I guess it's now easiest to look at the code. No, let's not look at code. I can go for each I in the non-zero pattern of AT. I can do C sub I plus equals, I'm mixing pseudocode and C, A I j times bj the scalar. So I'm going to do for each, no, it's bt I want to do, I'm sorry. I'm using the letter T. For each T in the non-zero pattern of B, remember B now is a column, only a column vector, this is what I have to do. Do you see that? So I can go through the columns of A and access this entry numerically and get its row index very easily. This is a scalar. I have to then multiply, and I can grab it here. I can just go through the entries, all the entries in the column of B, grab out the row index. So we have J equals BI of whatever, and BT equals BX of P. Okay, you put in some C code. I can get that entry out, and then I can go through this. This should be T, I'm sorry. I can get out the row index T that I need to use, and then get out the numerical value, and then then with that row index T, choose the Tth column of A, go through all the row indices there, and do this summation. And as I do this, I can also keep track of the set union. I can take, if you will, and do this. I have one new entry, potentially, in the non-zero pattern of the result. So here I'm computing both the numerical summation, which is over here, and I'm computing the set union, which I have over here. Next slide. Thank you. Over here. So I've got the set union and the numerical. It's kind of weird watching yourself on the TV there, but it's kind of handy. So this is an outline of the algorithm over here. And so let's think about the time complexity. Remember, this is only doing a matrix times a vector. Let's think about the time complexity of this algorithm. If we ignore the order m part to initialize this vector, okay, there's one more thing I have to do when I'm done with this algorithm. Actually, is this is accomplishing the scatter part. This is a scatter operation. I'm taking this row index and I'm scattering it into this large workspace of size m. When I'm done, I need to do the gather, and that's what's going to happen here for each. And I'm running out of letters. For each S in the non-zero pattern of C. You see, I've got this set, a list of entries, and let's hold off on a minute exactly how we're going to do this efficiently. This has to be done in constant time if we're going to do it efficiently. The set union. Okay. Let's hold off on a minute on how that should be done. But then when I'm done, if I've got this list of entries in this set, I can go through each of the list, and then I can do a gather. I can gather the row S and its value C of S into a sparse vector. So this, if you will, the set C, if I store it as a contiguous packed list, then it's giving me the non-zero pattern of the resulting column C. But the numerical values are stored in this large vector of size M, and I can't leave it there. That's just a temporary workspace. I'll have to throw it away, reuse it. I have to pack these results C down into a vector of numerical values that corresponds to the row indices of the set C. That's a gather operation. So this is what you see here as a scatter, and then this is a gather. Okay, is that clear? So scatter. So I'm going through, and you're going to see this scatter gather all over and over and over again for the rest of the class. If you don't understand this, read it or ask me or whatever. But it's very important that all this be done in the correct asymptotic time. If we then assume we've got this order M workspace pre-initialized and ignore that time for the moment, then the time complexity here is proportional to the flop count, this whole algorithm. Because, well, with some let's see, if we assume that every column of the matrix A has at least one non-zero in it, okay, then this is order flop count. I've got a nested loop here. So why is it order flop count? Well, here's the flops. So this is the touchstone. We have to do this work, and that takes constant time. So that's good. Let's assume for the moment that we can do this in constant time. If we can, then this whole thing then works fine. And we can iterate through every non-zero value in time proportional to the number of those non-zero values. Just iterate through that column vector. Iterate through all the entries in the column. Yeah.
Are we assuming parallel computation?
I'm sorry?
Are we assuming
Parallel computation? No, nothing parallel.
When you say scatter and gather?
What's that?
When you say scatter and gather?
Scatter and gather, yes.
Does it mean are you processing on different?
No, I'm not doing parallel computation. By scatter gather, all I'm doing with the gather scatter is if this is my workspace C, okay, then that is a scatter. And that's a gather. That's all I'm saying. So there's no parallel computation implied with the term scatter gather. But and actually when I'm doing the summation, I'm really doing a gather and a scatter because I'm taking out the value and then adding it and putting it back in again. So really this is, I suppose, a gather then a scatter, and this is a gather. It's important to note this gather gather pair of operations because it implies two things. One, it implies I've got a large workspace that's proportional to one of the dimensions of the matrices that I'm dealing with, or vector or whatever, which could be quite huge. All right, so there's a cost in terms of memory complexity to the gather scatter, which is size m. If I ignore the initialization time for this vector, which is another question, I'm going to defer that, then these both take constant time. So that's useful asymptotically. But there's one other aspect of this gather scatter is it can be very irregular memory access in terms of not, this is not an issue for asymptotic time complexity, but it's an issue for performance. You know, you're going through potentially bouncing along this vector all over the place in different order or different places. Okay, so this is costly. This is not a regular axis of memory. This is also an irregular axis of memory. So when you see a gather-scatter, you have to say, okay, the time complexity theoretically is fine, but the performance on any given modern computer is going to be at the speed of the memory bus, not the speed of the CPU, which is already a factor of 10 or 20 or 30 difference. Okay, it's really, or worse. I mean, it can be really bad. Doing a flop on the CPU is cheap compared to doing one memory read and memory write. Much cheaper, if that memory read and write is irregular. See, if you're doing stride, if you're going through some memory likes to be accessed like a Turing machine. You know, you just go through and very uniformly access those bytes. This one, that one, then the next one, the next one. Memory loves that. It's set up for that, and it'll work quickly. But if you do this, it will be very slow. So no, there's no parallel computing here, but there are concerns about how fast it will be in practice when you use gather-scatter. And so the sparse matrix algorithms use gather-scatter a lot. You'd like to avoid it if possible. Sometimes you can't. But when you see it, you know you're going to have some irregular memory traffic. And you just pay that penalty. So the next thing I have to, so let's finish off the time complexity here. The time complexity, I have to iterate through the non-zeros in B. So I've got time complexity already of the size of B time. I should put the size here. That's already accounted for. And now I go through each non-zero column here. But you see this work here then is time proportional to the total flop count. Because I don't have any extra overhead in this loop. For every iteration of this loop, I do 2 flops. Okay, and then if I can do this in constant time, then this whole thing in the body here, sum total over the course of the whole algorithm, will be order flop time. And then the same thing here, if every entry in C has to be computed, which it does, right? Every entry in the set C is corresponding to at least one pair of floating point operations, a multiplication and an add. And if I can do this in constant, if I can iterate here the body of this loop in each loop in constant time, then this is also no worse than this iteration here. And so the whole thing then, the whole time complexity is this. Order the number of non-zeros in B plus the flop count. So what that means is, I mean, think of the worst case. Suppose B is completely non-zero. All right? And suppose A is completely 0. You do no floating point operations at all, but you have to iterate through all the columns of B. So the total time becomes order, what is the size of B? Order K. So that could dominate. So if you have an empty matrix times a dense vector stored in sparse format, then you suddenly realize, whoops, I am doing more work than the floating point operation, but it's modest. And this can only happen if we make the simplifying assumption that every column of A has at least one non-zero in it. Then this goes away, because for every non-zero in B, we have to do at least one flop, and so this flop count dominates, and we have perfection. We have order flop count. That's as best as we can get, asymptotically speaking, because I have to do the floating point operations. So now for some details, how do we manage this set operation? This is kind of a fun trick. And also, we certainly can't initialize this vector C every iteration, because that'll kill us. Remember, I neglected this order m time. If I've got to clear this vector every single time, okay, then I'm toast. Every iteration, I would have to do this. I'd have to add to this plus m times the size of B. Oh my goodness, that's enormous. I can't afford that. I can't clear the whole vector C every iteration. You're toast if you do that. Okay, well, what I can do is I can clear it once. So let me add to this plus m. And there's even ways of getting rid of that, but that's, well, I won't go into that. So I'll initialize it once. So I'll set this workspace. I'll call it, what do I call it? I think I call it C, the vector. I'll set it to 0. This takes time order m. And there'll be some other order m initializations up at the top. So I've added some order m time here. So now I'm going to have a loop invariant. I'm going to assume at the top of this loop that the vector C is all 0. This vector C is this dense workspace here. I'll put a little bar in it to denote that. So I've got this workspace. So let's assume at the top of the loop that the loop invariant says that it's all 0. Well, if that's the case, then at the end of this iteration, I better clear the vector C to make it ready for the next iteration. Well, to do that, when you see down here, now you ask yourself the question, well, at the bottom of this loop, where is the vector C non-zero? Well, this script C here, this set, tells us precisely where the non-zeros are in this dense workspace vector capital C. So when you do the gather, to pull them out and to put it in your sparse compressed form, you can extract it from this workspace and then also set the thing to 0. So I can just do C of I equals 0, and I've not increased the time complexity of this iteration. Yeah, you can see that at the bottom of the slide. And I've satisfied my loop invariant. So I can initialize it once and then let each iteration initialize it for the next guy, for the next iteration. And, even more importantly, at the end of the iteration, the vector C is all back to 0. Why should we care? Aren't we done? Well, maybe not. What if we've got other matrix computations to do and we need another workspace of size m? Well, in one of my sparse matrix packages, MATLAB doesn't exploit this. You've got a big sparse matrix, and the dimension of this matrix, you're doing lots of things to it. The dimension's not changing. So what I have is I have some workspaces lying around of size m or n or whatever, and I keep track of how big these workspaces are. And I know some of them are, one of them is a double precision workspace of all zeros. And initialize it once at the top of my entire algorithm. All computations start. Okay, we're doing matrix computation. We've got size m. Okay, here's a vector of size m, all 0. Do some work, use this vector, and then return it to 0. So it's initialized only once at the beginning of the entire program. You do another matrix multiply, do another one. Every time you do something, you use this vector, but when you're done with it, you set it back to 0 again, and you only pay the initialization time once for your entire program, not per matrix vector multiply or matrix multiply, but once in the entire computation. So this gets amortized across. You could do thousands upon thousands of matrix multiplications, and you only pay the m time once. So this basically goes away. So this we don't have to worry about. And if we make the simplifying assumption, that's why I said I can ignore this. That can go away. And then if we make the other simplifying, although in my code you'll see here in C-Sparse I don't exploit that fact, so I'll leave it in. And if we make that assumption that every column of A has a non-zero, then we can ignore that. So it's just, again, perfection. We're down to the flop count. So the other trick here is how do we do the set union here? How do we add a single item to a set? We have to know two things. If we want to add an item that's already there, we don't want to add it twice. We'll want to keep track of how big this set is. We want to have a list here. So there's really two things we have to keep track of. There's a list of entries. Okay, but I want to add to that list in constant time. Add a new entry to the list in constant time. If it is not in the list, I've got to append it to the list. But if it's already in the list, I better not append it, because then I'll get a duplicate. And I don't want duplicates. All right. So how do we do that? Well, we need another order M workspace, and I'll call it, it's going to be binary for the moment. I'm going to change it a little bit, but I'll call it W in the code. And it's the size 1 to M, and it's just initially false. Okay. So if you will, it's a binary workspace that's all false. And whenever I do the set union, I look at WI and ask, well, is it true or false? If it's false, I set it to true, and I add I to the list. So the set union would look like this. If WI is false, then append I to the list C. So C is a set, and I'm storing it just as a list. And set WI to true. And there. So this is constant work, constant time work. And this is what's going to do this set union operation right here. And now all I have to do is iterate through that list, and we're done. So, but again, we have another problem here. We have to assume at the beginning that W is all false. But again, that's not a problem. We can say, oh, C is all 0, and we can assert here that W is all false. And at the bottom, we could do the following. We could say WI is false. Okay? However, I cheat, and I don't have to do this, and I'll show you in a moment how I cheat. And at that point, it's easier to look at the code to do that. But instead of, well, no, let's not look at code. Let's look at the chalk first. What I do here is I cheat. I don't use a binary vector. I use an integer vector. And I assert at the top, the loop invariant at the top says, where is it? Oh, wait a minute. Oh, I put my loop invariant in the wrong place. I'm sorry. This doesn't make any sense. It's not, for this step here, it's not really a loop invariant. It's up here. That C is all 0 and W is all false is a condition that's going to exist at the top here. But when I'm done, I want to come back to this invariant at the top of this whole algorithm. The reason being is that this algorithm is only computing one column of C. But I have lots of columns to compute. So I'm going to reuse this algorithm for every column of the C matrix. C is no longer a vector, it's now a matrix. So I'm sorry, this loop invariant, I put it in the wrong place. Here it has to stay non-zero because I'm working on it, I'm adding to it. Let's see. I need to, I'm sorry. It's so much easier to look at it in code. This loop here has to terminate here. I'm getting myself, so I'm not working on full thrusters today. I had a pretty crazy weekend. I took my daughter into the hospital for an appendectomy, so I'm kind of low on sleep. Okay, so this gather operation happens when the entire work is done. We've done all the scatters. In other words, we've done this summation across all of the B's, and then when we're done, we need to pack the C vector down into a single compressed result. So at the top, C and W are all 0, and at the bottom, C and W are all 0. I go through each here. I do the summation here for every entry in B, and go through A and do the scatter. Okay. And then when I'm finished with the summation, I've got to pack the result down, and that's where this gather occurs. So W starts out as false, and then at the very bottom it's ending as false. But so the W vector, I use a trick. Since I'm using these arrays, a total of, let's see, how many columns are there in C? N. So there's going to be, when I'm doing the matrix multiplication, C equals A times B, there are n columns of C to compute. And at the top of that iteration, this W vector has to all be false. And so what I'm going to start out with is a vector of zeros. So that takes order m time to initialize, just like C did. But this Wi is false and set it to true. I'm going to exploit the fact the loop invariant will be slightly different. The loop invariant at the top will be that all the entries of W are less than or equal to n. I'm sorry, not n. What am I iterating? Let's call it, I think I call it j. Yeah, j. If I'm computing the jth column of C, the loop invariant will say that all the entries in W are less than or equal to j. So the test of falsehood will be if Wi is less than or equal to j, then that predicate is false. So this becomes this. And then to set it to true, I set it equal to j plus 1. That's truth. Wi equals j plus 1 means it's true, and it's false means Wi is less than j. Okay, so there's my Boolean test, my predicate. Now, think about what happens on the very next iteration. J is incrementing by 1. When j increments by 1, magically, all of W becomes false. Because now when j increments by 1 to compute the next column, suppose j is 10. All the entries in here are less than or equal to 10. And I'll use 11. I'll put an 11 here for every entry I want to mark. Now increment j. J now becomes 11. So now the loop invariant says that all these entries are less than or equal to j, which is now, so they're all false. So I clear the array in constant time by changing j. And I know j is incrementing from 0 to n minus 1. So I do not have to, I can skip this step at the bottom. This now becomes implicit. Setting Wi to false now is implicit. And this truth at the top now is satisfied. Okay,
why not do the same thing for the C set?
The C vector or the C set?
Yeah.
Well, the set's easy because that's just the set. Well, the set is really represented in two ways. It's represented in the scattered form with this W vector. But then I have this also a list of entries. But see, it's easy to set a list to empty. You've got a workspace, okay, and you're just appending to this list, and you keep track of how many entries there are, and at the end you just set that to 0, and you're done. So clearing the set itself is easy. The list of entries, to say it's empty, you just set the size to 0, and every time you add something, you just add 1 to the size. So there's two ways that this set is represented. It's in a packed list. They're just appending to it at the end. Of course, then at the end of the computation, that's going to be the result, the list of row indices and the result. Okay, so I'm not actually clearing it, I'm keeping it. Okay? In fact, I'm going to keep that as part of my C matrix. I'm building my C matrix. Right? I want to keep this, I don't want to clear it. All right? But the W vector I have to clear every time. That's the scattered form of the list. So I have a list that's packed, and I have a Boolean vector, if you will, this W vector, which says if I is in the list, then Wi is true. If I is not in the list, then Wi is false. So this is a scattered form of this list. But I need to clear it, and to clear it, I can clear it in constant time with this trick. It doesn't improve the asymptotic complexity. But it cuts out a step. It cuts out a scatter, and scatters are expensive because of irregular memory access. Okay, so now, finally, let's look at the code. There's a lot of explanation for just a little bit of code. Here's the code, part of it anyway. And so I've got this. This is just mechanics up here of extracting the input matrices A and B. Now again, I'm doing matrices, not vectors. And then I have 5 minutes. Okay. This vector C with a bar through it, I'm actually calling X. I apologize. I should have used the letter X here. So let me change this here to an X. I spallic a matrix. Now, this is the curious part, I do not yet know how big my output will be. So I'm going to use this notion of the dynamic table, where if I run out of space, I'll double the space. Okay, we talked about that. I talked about that last class, or several classes ago, about how to manage a dynamic table when we're looking at the triplet matrices. And now I'm going to use it for this compressed sparse column matrix. So I spallic it, and I just give a guess as to the size. Now I'm going to go through every column of C. The first thing I'm going to do is, well, is it possible that I could run out of memory? NZ is keeping track of the current number of non-zeros in my matrix output C. And I could, at worst case, append M non-zeros to it in the set script C, which is really just the end of this C matrix. And so, well, if I might run out of space, then I'll spree-allocate it and I'll double it. I'll double it and I'll add M, because if it starts out not proportional, it's important to at least make sure that I have M space there. So I'll spree-allocate. And if I'm unable to spree-allocate, to double the memory space, double plus M, then I just return failure and I run out of memory. At this point, then, you have to reacquire the CI and CX vector, because it's possible they could have just been moved. So that's why this line of code is there. Now I'm building the jth column of the C matrix. So I've got to keep track of where that jth column starts. And now I've got to go through this pseudocode over here for each T in the set B over here. Okay, that in code now that becomes this. For P equals BPJ, P less than BPJ. This is like you're going to see this loop over and over and over again in almost every algorithm. I'm going to go through, and I gave this function, since I'm going to use it other places, I call it a CS scatter. So CS scatter is going to do everything inside here. That's doing this scatter. And then I have to, when I'm done, and I'm sorry, in the first iteration I put this inside here, but it has to be out. When this body is done, I've got to do the gather. And so that's what this is here. This is the gather. But it turns out just to be a single line of code, because I don't need to clear the W array. That's happening inside the scatter function. You see, the W array is starting out to be it's callic, so it's all 0. And then I need to keep track of where the last column ends. So CP of n equals NZ. Don't forget this. If you forget that, you have an incomplete sparse matrix and it'll be broken. And then I trim off the excess space and return the result. And we're done. So let's look at this gather function. And I've got about a minute, so I'm not going to be able to really finish it. Whoops. So this is the scatter function. This is this whole body of loop here. I have to go through. This is for each I in the particular column I'm interested in, which is, I'm calling it here J again. I'm reusing the J. The J here is not the same as the J above. Maybe I should have called this T. Whatever. It grabs that, and then it does this if else if kind of this if it's false test. So this body of work right there is this right here. If it's not in the list, then add it to the list. And I get away from, you asked the question, well, can we avoid the setting of C to 0? Or as I'm calling it now, X. And I think I'm out of time anyway. And I'm actually going to avoid this entirely. Okay, I'll call this X. And I'm going to assume that's initialized to garbage. There's nothing. I mean, this is complete wreckage in there. And now I can use my result here, my pattern to say, well, if this is the first time I've seen this row index I, then assign it. This is not this is not a plus equals. It's an assignment. It's an assignment because this is a new entry. So I'll just write it there, not add. So it overwrites what the gunk that was there. Otherwise, if it's already there, then I have to do the add. And so this distinction now avoids the fact that this vector C has to be initialized to 0. And then this right here gets nuanced into two different cases. But it's a minor change and allows us then to start with a double precision vector, which is not just 0, it's gunk at the beginning. And that's easier to work with. You can just allocate it in constant time and it's uninitialized. You don't have to zero it out. So the order m time for the x vector gets entirely removed. And then I can skip this step here of setting it to 0 and I'm done. And all I have to do is do the gather, which is one loop. So, which is the previous slide. So that's it. And we'll look at matrix addition next class. Thank you.